record this from here. So today's, we've only got an hour and we used quite a bit of it. Today, the very first thing I wanted to do was just do a slight overview of exactly what organic synthesis is. And then next class, we'll talk about the retrosynthetic analysis. So there's loosely two broad categories of organic synthesis. One category is it's funny, the spotlight doesn't work on PDFs for some reason. I don't know. One is a targeted, where you've got a target that you want to make. And the other is you've got a method that you want to use to make something. And those are basically the two broad categories of it. Now, what we're going to see for most of our class is the targeted approach, because what we are going to be looking at is there is some natural product that we want to make for some particular reason. Now, some research groups actually combine the two things. They've got a certain method that they want to exploit, and they use it to make a natural product to say, oh, this is a very useful reaction, and here's an example of us using it to make this natural product. So, so you've developed some special reagent, or you've developed some special catalyst, and you apply it to something. So, but the whole process of developing a method is fascinating in its own little sort of way. So there's the way that current funding to science works, you seem to get a lot more research money, research dollars, if you employ this type of methodology. Anyway, that's my commentary on funding for basic research. Now, the targeted directed approach is fascinating. Basically you find some natural product that has some sort of really interesting, say, biological activity, and you want to derivatize that molecule to make it even more potent. And so what better way to do that is to make it and then derivatize it. That's sort of the other sort of way, is that you have a specific molecule that you want to design, and these can be for some sort of theoretical interesting molecule, biological or medicinal, or material science. There was a former colleague in the department who was in inorganic chemistry, who was basically trying to make molecular magnets using a combination of organic and inorganic chemistry. And so his whole approach was material science sort of thing, making molecular magnets. And that would be, it was fascinating sort of research. So those are basically that's just basically oh, there's my little laser. That's the broad overview of organic synthesis. When I was in graduate school, there was a specific natural product that our research group was trying to make, and there was a specific method that we wanted to make it through. So it was a combination, but the method was well designed up earlier on. So it was basically I would call it a more target directed sort of approach for that. Okay, now the next part. So if we look at the grand history of Nobel Prizes in chemistry, this is just a list of all of the Nobel Prizes that basically are associated with organic chemistry. So we'll see a little bit later that Emil Fischer, turn of the century or the turn of the last century, was making sugars and pyrene synthesis. We see in 1912 our friend Victor Grignard, which we all know about the Grignard reagent. So that's so this was developed over 100 years ago. Paul Saboteur, so hydrogenating organic compounds in the presence of finely disintegrated metals. So this is the forefather of hydrogenation chemistry. And then there's a whole bunch of synthesis around biologically important targets. Let's see, where will we go next? Robert Robinson, investigations on plant products and biologically important, especially the alkaloids. We will see what alkaloids are a bit later on, and Robinson's got a very special reaction that bears his name, which we'll talk about. The 1950s, here's our friend, the Diels-Alder reaction. So this was the discovery and development of the Diene synthesis and that key reaction associated with it. Ziegler-Natta, they, of course, the technology for making polymers. So they've got that Ziegler-Natta catalyst for, you would have talked about that in inorganic chemistry, I would imagine, at some stage. I'll take that as a yes. R.B. Woodward, so achievements in the art of organic synthesis. So Robert R.B. Woodward is basically the demigod of organic synthesis. There's going to be lots of things that we'll see with regard to his group. Derek Barton, this was interesting that, so development of conformation, its application to chemistry. So we did do in organic 3 and organic 2, we talked about conformational analysis with regard to like a whole bunch of different, like I think in organic 3 we would have talked about allylic strain and that type of stuff. So there's that whole area of conformational analysis, and it's basically application to chemistry. So, and Derek Barton also had some fascinating radical chemistry, which we'll talk about a bit later on. Prologue, Conforth, and if I put the name Ingold in there, these would be the, we've heard of them through their, when we're using those rules to assign a configuration at a chiral center. And so, but they won the Nobel Prize for stereochemistry of organic molecules and the various reactions for it. So that's interesting. George Wittig, Herbert C. Brown. We have seen Wittig before, I think, with regard to the Wittig reagent. So, and H.C. Brown, boron, we've seen certainly boron in synthesis, and of course phosphorus. So that's those two there. Bruce Merrifield, this is solid phase chemistry. This is quite revolutionary, particularly now in the field of peptide synthesis. We could have a whole course on solid phase chemistry. So if you're working on peptides, there's a very good chance, and now this is all automated, you can do a whole thing of peptide synthesis. But Merrifield, there's one resin which bears his name. Basically, what you do is you attach your small molecule to a resin, and then all of the aqueous chemistry which takes place, you can wash it away because what you're looking for is attached to the resin. And then when the time comes at the end, you can just chop your molecule off the resin and you've got a pure, so it removes the need to purify things and that sort of stuff. So that's really neat stuff. Then I guess the next name, which we'll see soon, is E.J. Corey and development of the theory and methodology for organic synthesis. So we're going to talk about his retrosynthetic analysis later on. carbocation chemistry, and then there's a whole bunch of people which discovered the fullerenes. I put them under the chemistry banner, organic chemistry banner, although some of them would have been physicists, so that's kind of funny. Knowles, Norrie, and Sharpless, they worked on catalytic hydrogenation reactions. That's chiral or oxidation reactions. Barry Sharpless and his group developed a way of making chiral epoxides or the dihydroxylation reaction. And then Grubbs and Schrock and Eve Kevin, they developed metathesis reactions in organic chemistry. Now, this is a fascinating sort of thing, which we'll see in one of our synthesis as well. So I've taken this to 2005, and we are now in 2020. So we've got approximately 15 years of chemistry Nobel Prizes to look up. So if you want some bonus marks, dig up if there's any organic chemists between 2005 and 2020 that have won the Nobel Prize. That's just a take-home little thing for you if you want to do it. And here are some of the early syntheses that took place, some of the molecules that are important. So the Urea synthesis, this basically changed the way that science or chemists at the time, I'll say thought that the world worked. Okay, so urea comes from a living organism, and there was a theory at the time that only living things would make organic compounds. So, and that being alive carried a sort of essence, some vital ethereal essence that was important for, how do I explain this? That you needed to be alive and you needed to have this essence to be organic compound, and you couldn't take something that didn't have this essence and convert it into something which did have this essence. And so Woodward basically proved that wrong. He took an inorganic compound, heated it up, and created urea. And so that basically torpedoed that entire theory of, so that's basically torpedoed the live essence theory. It's probably not called the live essence theory. I'll have to go back and look at my history books a bit better, but anyway. So some of these people we have won the Nobel Prize that we talked about. Perkins, there's a couple of syntheses for Perkins. There's a journal which is basically named after him, an organic chemistry journal in England. I think they've renamed it since that time. So Robinson won the Nobel Prize earlier, talked about that. Here are some of the interesting things. So the other Fisher won the Nobel Prize for the synthesis of this relatively complex molecule here, long time ago, right? Almost 100 years ago. And then our friend R.B. Woodward and Doring, they both won the Nobel, Woodward won one Nobel Prize. He would have won two if he'd still been alive. There's that rule that you can't be deceased to win the Nobel Prize. I think hopefully they change that one day because it's a bit silly. Let's go back. This Nobel Prize here in 1981, if R.B. Woodward had been alive, he would have won that because it was both him and Roald Hoffmann which designed one of the key theories for orbital symmetry in organic chemistry. So that's, anyway. Quinine, where do we find quinine these days? Does anyone know?
In soda? Like club soda or something?
Right, in tonic water. So it's the bitter component in tonic water, and they add a bunch of sugar to it, and it makes your gin taste delicious. So it's a naturally occurring alkaloid, and it's an anti-malarial compound. So the when whole colonization was taking place, you could find this in South America. It's quite an interesting story. And so there was a push by the Europeans to basically find the plant which produced this stuff and control that area, because they'd put it in water so they could drink it to prevent malaria. And it grew better in South. I think they tried to transport it to India to grow it there and that sort of stuff. But it's a fascinating story. I'll try to dig up the rest of do a little history class on that. But anyway, so quinine, it's quite delicious with gin. All right. Now, okay, so the last little bit, we got a couple minutes left here, just to finish this off. So synthesis basically comes from the Greek for putting things together, and there's a number of different ways that organic chemists have classified synthesis. So one method would be a straight up linear synthesis. You start with A, you make B, C, D, E, and then you have your final product. This is, it works. One of the key problems with this is that at each step, there's a yield associated with it. And the longer the linear sequence, the further the yield goes down. So if you've got 5 steps and your yield is 55% each step, your overall synthetic yield is going to be 77%. If it's 55%, it's going to go down to 5. So you're going to have a hard time having enough material to finish things off. A different type of synthesis, which would also have 5 steps, would be a convergent synthesis, where you've got 2 starting materials and you've got, you make 2 intermediates, and then those 2 intermediates are glommed together to make your final product. Now, the way that the yields are calculated for something like this is that it's the longest linear sequence. That's what the total number of steps would be. So if you've got 5 steps in a convergent synthesis, your yield could be up to 18%. So because 1, 2, and 3. And you'd always use the lowest yielding steps to calculate this. So the advantage is they're shorter, typically higher yield, easier to execute, and you can bring more material along. So that's a convergent synthesis. A divergent synthesis is if you make a common intermediate and then you derivatize it by making 3 different things. So we're going to see an example. We're going to see actually a couple of examples of this. These are really pretty. If you can design something which you can make a series of products from a common intermediate. And what would be cool is if it was convergent to this point and then you just ping off the rest of them. So that's what a divergent synthesis is. And that's really useful for derivatizing something. Now, in the literature, you'll see things like total synthesis. So this means that you start with a common, readily available starting material, and you make some natural product. And they can be enantioselective synthesis. So you'd put the enantioselective in front of it. So this is this isn't chiral, but somewhere along the line you install this chirality, and you can do this through a number of different ways. Sometimes it's starting with something which is chiral and making something that's chiral, or you've got some chiral catalyst or something like that. So that's what a total synthesis is. And then there are partial syntheses. So you start with an advanced intermediate, and then you make your final product, like Taxol. Yeah, it was a big race to make Taxol. It was interesting. That's a fascinating little. We'll talk about that a bit later on too. And then there's things like start with penicillins and make cephalosporins, that type of stuff. And the last but not least is what we would call a formal synthesis. So somebody has made this natural product and they have used this step to make it. So the pseudoadomic acid A, and they started from here, and they used MCPBA to do the epoxide. So let's pretend that you make this compound here. You can say to yourself, well, we made this and we know that this last step works, so we'll just publish this as this step, because maybe you did it some other way than the original, and you would call that a formal synthesis. So you're not actually doing the last step because it's a known transformation on that particular molecule. Yeah, so that's basically, if you ever hear the term formal synthesis. So what we'll do, what we'll start next class is how to, because this can be quite complex, where to start from and this sort of thing. So what we'll see is that how to tackle making some sort of complex natural product. Yeah, so that's what we'll do next class. Were there any questions at all? This stuff's all on Moodle already, so it's just not there with my highly biased commentary. But yeah, if you can think of, if you can send me, if you want to do a little mini sort of thing for some bonus marks, let me know which chemists have won the Nobel Prize in organic chemistry specifically over the last 15 years or so. And I know there's been a couple because I can think of some off the top of my head. All right. And everyone should have got the email about that little dry lab thing to try too. So that'll help us prepare us for what we're going to do in the coming weeks. I'll post the other actual experiments later today or tomorrow morning. All right. I will take that as a yes. Okay. Well, have a good day, everybody.
All right.
Bye.
Have a good day, Dr.
You bet.